Get there in the end.
Right,
Okay.
we can go, Debbie. Brilliant.
Thank you. So yeah, I just wanted to say before we move into the main bit of it, this is the first jointly hosted guest speaker session across the Peninsular Trauma Informed Network. So Plymouth's obviously hosted a lot of guest speaker sessions before, but this session has come out of the conference because Haley approached us through her involvement in the conference to say that she'd be interested in doing this guest speaker session. So this is our first cross-peninsular guest speaker session, which feels really, really good, and, you know, more work in our kind of regional collaborative work, which is great. So yeah, just wanted to start off with that.
Yeah, that's brilliant, Debbie. This is such a treat for us all today, and yes, such a privilege to have Haley Peckham come and speak for our shared networks, our Peninsular network. So Haley's background includes philosophy, mental health nursing, psychotherapy and neuroscience, and is very much grounded in her own lived experience of recovering from complex trauma, which she will be talking about today. So we need to hold that sensitivity in mind. But while studying philosophy, Haley worked with children and adolescents in care and later trained as a mental health nurse at King's College in London. Struck by the enduring impact of early trauma and neglect, Haley studied molecular neuroscience at Bristol and gained her PhD from the University of Melbourne. And that's where I first came across you, Haley, was one of your presentations that you did whilst you were in Australia that was just struck me and was incredibly profound. And I love your delivery style. So very much looking forward to this morning's session.
I didn't know that.
Yeah. So since realising that evolutionary biology and neuroscience are critically important for delivering coherent, ACE-aware and trauma-informed approaches, Haley has shared her learning with professionals across statutory services in Australia and the UK. She's currently working with Zebra Collective and did a wonderful workshop for us for the Peninsular Trauma Informed Conference back in July with with Professor Luna Donazell, who's another friend of the network, and Haley and Luna are delivering shame competence training with the police at the moment, aren't they? So you've got lots and lots of things going on, Haley. But if that's all right with you, we will make a start. People are still joining. Yeah, switch your cameras off if you feel more comfortable with that, people. Get comfortable and let's go, Haley.
Great. Thank you very much for that introduction. Let me just make sure I can still see you all here. Okay. So I think that you can see my screen. Vicky, could you give me a thumbs up if you can see the right screen? That's awesome. All right. So thank you for that introduction, and what a privilege to be the first guest speaker across the network. Thank you. I very much enjoyed the conference. I thought it was sort of groundbreaking that we're doing this. So very, very happy to be here today. And I will be talking to you about some insights from rabbits and elephants. But don't get too excited because they don't come until a little bit later on in the piece. So as I said, it falls into 3 parts. And these are the 3 parts that it falls into. So firstly, I'll be talking to you about how experiences build brains. And then I'm going to move into relational experiences, how relational experiences build brains, but I will do that from my own lived experience. So just talking about the kinds of experiences that got me into tricky spaces and the kind of experiences that brought me out of them too. And then lastly is where the rabbits and elephants come in, and that's when I talk about how experiences set us on a life history trajectory. So we'll get to that in due course. So this is my assertion that experiences build brains. So I like to talk about neuroplasticity, and when I talk about neuroplasticity, I'm not really talking about recovery from injury as such, although that it is part of that. What I'm talking about is the normal processes by which experiences shape brains. And it's useful here, I think, to proceed with a water metaphor, thinking about experiences as being like raindrops. So each experience, like each raindrop, is not particularly significant, but en masse, they do make a huge difference. So rain falls and collects, and experiences sort of fall on the brain and collect, and then they travel down pathways. And as the water does so, it sort of creates this channel. And the same with experiences. They form these neural pathways. And that means the next time experiences fall or that rain falls, they'll go down the channels that are already there. And what that means for the landscape, as well as the landscape of our brains, is that experiences and water sort of shape the whole thing. So our brains are profoundly shaped, if not built, by our experiences. So I'm going to take you through 4 mechanisms for how that works. Now, I want you all just to settle down. Just let this be a story and let it flow over you. It doesn't matter if you don't take all of it in. There are some sort of key messages that I think that will come through. So don't worry too much about the detail. And I quite often spend a whole day teaching people this. So just let it come to you as it does. So I'll go through epigenetics, which I'm sure many of you have heard of, which is sort of shown on the top left picture. Top right picture is neurogenesis. Bottom left is synaptic plasticity, and the bottom right is white matter plasticity. So epigenetics. Epigenetics is terribly exciting. It's about how genes learn from experience. It's the sort of quintessential way, really, that that nurture interacts with nature. So for those of you that didn't do A-level biology, and for those of you who did it quite a long time ago, what happens is on the DNA, we have genes. We have about 20,000 genes, more or less. And the genes are held on this DNA, which is all sort of like a library. And then the RNA is like a student that goes into the library to get the information. So the RNA is then carried out of the library, rather like a book, if you like, or a recipe, and then made into a protein. So the genes are on the DNA, the RNA is a copy, and the protein is the finished product. And that's sort of biological dogma. It's kind of how we are made, if you like. So epigenetics means above the gene. So the DNA and the genes themselves are not changed. Something happens above the gene or beyond the gene. And what it is it's small chemical groups that attach either to the DNA or to histones. And what this does is it makes the genes more or less accessible. So the library is or isn't open or closed. It makes them more accessible to transcription machinery, which is the RNA. And what it actually does is it acts as a volume control over the genes. So these changes in gene expression, so the gene remains the same, but the change in gene expression may persist from minutes to a lifetime, and it may even persist into the next generation and sometimes the next generation after that. So here's an example. I'm sure every person here, however many of you there are, I'm sure every person here has heard of cortisol, which is the stress hormone. Now in rodents, that's corticosterone. But the bit that we don't talk about very much is the glucocorticoid receptor. And in rat pups, something that we have come to understand is that the glucocorticoid receptor is epigenetically regulated by early maternal care. So mother rats lick and groom their pups. They have high levels of licking grooming or low levels of licking and grooming. And what they've found is that high levels of licking and grooming change the glucocorticoid, the epigenetic marks on the glucocorticoid receptor gene so that it's more accessible. So there are more glucocorticoid receptors for a rat pup that's had a high level of licking and grooming. So what that means is when the stress response, when cortisol or corticosterone is activated, it travels around the system and it lands on lots and lots of receptors. And what that also means is the response is swift. It turns on a lot of genes itself. It also means that that response is shut down quickly through negative feedback loops because it's landing on so many. So then those receptors are taken up. And so the cortisol or corticosterone is removed from the system. So it's a very fast and efficient stress response, easily turned off. On the other hand, if you have a mother who isn't, for whatever reason, able to offer the same amount of licking and grooming, that permissive epigenetic mark is lacking. So what that means is there are fewer glucocorticoid receptors. So what that means is that the corticosterone circulates for longer, which turns on a different set of genes. So it has a different kind of outcome. But in circulating for longer, because the negative feedback doesn't work so efficiently, it also means that those little rat pups are stressed for a bit longer. Now you might think, oh, that's no good. But on the other hand, if for some reason mum is a bit less available, no blame here, just a bit less available for whatever reason, That stress hormone keeps us alert, helps us learn, and makes us pay attention. So actually, that can be an extremely helpful thing. So what I'm saying here is that the experiences that we have in the world can lead to these adaptive changes, just as we see in the rat pups. Now, we don't know if anything exactly like that happens in humans, but it would be unlikely that there aren't similar mechanisms. So moving on to neurogenesis. So neurogenesis is about the growth of new neurons and their successful integration into the existing network. And it's thought to underlie process of new memory formation and changes to existing memories. So this little guy is a black-capped chickadee, and he is a food hoarding bird. And they do lots of studies of neurogenesis in food hoarding birds. And one of the things they find is that neurogenesis increases in harsh environments and reduces when the birds are in captivity. So what happens in these birds is they have a higher rate of neurogenesis, which is thought to be linked to learning and memory, in the autumn. Now that's standard for all of the birds. However, if those birds are in captivity, that happens anyway. If those birds are in a benign environment, they still have an increase in neurogenesis in the autumn, but the harsher the environment, the more scarce the food, the more reliant they are on remembering where they've hidden their dinners, the higher the rate of neurogenesis. So again, what we're seeing is experience in the environment leads to these changes that are adaptive. They help these birds survive. I'm sure you all have heard of the neurons that fire together, wire together, which is a sort of quip about Donald Hebb's work. So I don't know if you guys can see me, but if this neuron fires and it's strong enough to depolarize this neuron, then that junction between them, which is the synapse, gets stronger. So this one fires, that gets stronger. If this one fires and it's not sufficient to depolarize this neuron, then that synapse between them, the junction between them, gets weaker. And that is the cellular basis of learning and memory, or the accepted cellular basis of learning and memory. Now, Eric Kandel and his team got a Nobel Prize for looking at synaptic plasticity in the Californian sea slug, which they describe as having a simple nervous system of 20,000 neurons. So what they did with this little guy is they used the experience to alter the reflexive behavior. So if you touch its tail, then it withdraws its gill. So what they did was they sensitized and they habituated it. So sensitize, or do habituation. So when they habituated, they touch the tail gently and the sea slug gets used to the tail being touched gently and withdraws the gill slowly. Or they sensitize it. And so then they administer a slight electric shock to the tail, which makes them withdraw the gill much faster. So both of these are experiences, and they are learning experiences, and they tracked the learning that happened down to the synapses in the junctions. So again, what we're seeing is experience in the world, in this instance, is directly translated to particular identifiable synapses in the Californian sea slug. And lastly, on to white matter plasticity. So you guys can probably see that I'm holding up a bit of a cable here. You know that there's copper wire in there that transmits electricity, okay? And this wrap around it, this rubber around it, is there precisely to insulate that. We're insulating it so that the signal doesn't leak away, so it gets to where it needs to go. The insulation is a critical part of this because it protects the signal. Exactly the same thing happens in biology. So myelin is an insulator that increases the speed and conductance of nerve impulses down axons. So going back to my metaphor, I was talking about how water sort of shapes the landscape. Essentially, if you've got an awful lot of water running down a particular path and you really want to make sure it's going that way and none of it escapes, what you do is you build a pipe. And that is a perfect metaphor for myelination. So we can image white matter plasticity, which is myelination. And what we find is that if we image the brains of piano players, people who've been playing the piano for a very long time, you can see that they have more white matter in their fine motor cortex. Now, that's because this is activity-dependent myelination. So all of those years of practice of moving your fingers in the right way to touch the right key to make those beautiful sounds, all of that builds up white matter in that area of your brain through practice, 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 practice. Now, one of the very interesting things about this is that sometimes we use imaging to study the differences between the brains of clinical populations against non-clinical populations. So we might look at the brains of people who have depression or borderline or schizophrenia or bipolar, and then we might compare them to the brains of normal people, okay? People without these diagnoses. But what happens then is if we see that there's a difference between those two groups, we might think, oh, well, that must be the deficit or the difference or the pathology in the brain, because it's a real thing, right? But what happens is when we do that, we're not accounting for the effect of experiences on the brain. And I'm sure you'll agree with me, playing the piano isn't clearly not a pathology. So we notice, as well as piano playing, we see changes in white matter when even doing 2 weeks of a meditation course, in learning to juggle, in driving a car, in practice mental arithmetic, in learning a second language. Practice and rehearsal take shape in our brain. So again, what we're seeing is our repeated experiences take shape in our brains. So this is the conclusion that I draw from this, is that neuroplastic mechanisms, which are evolved mechanisms, turn our lived experiences into biological adaptations that help us to adapt, survive, and reproduce. And that brings me to the end of the first section on experiences build brains. So I'll just stop sharing my screen.